Okay, now we are going to a few MCQs from electromagnetic induction. Electromagnetic induction, and so far we have learnt Lenz law and Faraday law. When you combine both together, we came up with an equation like this, that is E induced equals minus d phi over dt. Now this is what we have covered so far. Induced EMF. So we'll be using this equation basically, most probably, and then the other equations we learned. What is the other equation we learned, people? E equals BLV, right? E induced equal BLV. This is the electromotive force induced in a wire moving in a magnetic field. Moving in a magnetic field. All right. Fine. So now let's focus on this question for the time being. 2006. The circuit shown is placed in a uniform magnetic field that is acting into the page. This magnetic field is decreasing in magnitude at a rate of 150 Tesla per second. Now, key facts. Magnetic field is this magnetic field is decreasing. So already existing magnetic field decreases. Already now we are applying Lenz law. We are applying Lenz law into a scenario. Already existing magnetic field. What is happening to that magnetic field? Reduces into the plane. If the already existing magnetic field reduces into the plane, what should happen? So newly induced magnetic field should be created where? Should be in what direction, guys? Should be, it is reducing into the plane, means should be directed into the plane, same direction. This is what Lenz's law is. If the change is reducing according to Lenz's law, the induced current or the induced induced magnetic field will try to oppose it. So if it's trying to reduce inside, we should try to increase it into the plane. If it is trying to reduce into the plane, so the induced current will try to increase it into the plane. Therefore, this then as usual, as I mean, just like we discussed, the induced is like this. That is the induced magnetic flux density. If that is the case, then what about the current? Current should be according to the right hand corkscrew rule, current must be in this direction. How? Clockwise. Current must be clockwise. Current must be clockwise means now we have to consider an EMF. Now EMF will be in this direction, induced EMF, clockwise direction, induced EMF. So it's like you're going to put a new battery this way. So I'm going to put a new battery this way. All right. So how are we going to find this? For that only we are going to use Faraday's law. I just use Faraday's law. Magnitude of induced EMF. It's going to be rate of change of magnetic flux. What we know. So equation is going to change. dB or dt, right? And what is this A? A is area of conductor inside magnetic field. And dB over dt, it's given to us in the question. Yeah. From this we can find out the area. Now we will area. How? Area of the conduct inside the field. It is going to be 0.1 into 0.01 meters squared. Let's finish it off. Okay. We have found the magnitude of induced EMF, which is 1.5, and it is going to be, now this current is going to go, the current due to this battery is going to go counterclockwise, but the induced EMF is clockwise. Induced EMF is clockwise. We have found it applying Lenz's law. Now for this circuit, what I'm going to do is I'm going to apply Kirchhoff's principle. For this circuit, let's apply Kirchhoff's principle. Kirchhoff's law. Okay, for this circuit, Kirchhoff's law. How do you put Kirchhoff's law? Sigma E equals sigma IR, because they are asking us to find out the current, and I will apply the equation in the counterclockwise direction, because the battery with the high EMF is 5 volt, so it is going to be 5 minus 1.5, because 5 volt here, the 5 volt part is clockwise. This 5 volt, it is like clockwise, the 5 volt is clockwise, but the other EMF is no 5 volt is counterclockwise, anti-clockwise. This 5 volt, it is anti-clockwise, sorry, is anti-clockwise. It's going to give out an anti-clockwise current now, people. But this one, the induced one, is clockwise, therefore they are in the opposite directions. It should be 5 minus 1.5 equal to, current is I into, there's only one resistor I can see, 10 I hope this does not have internal resistance. See there, okay, so it's 3.5 equal to 10I. Therefore what is the current? Current is going to be equal to 3.5 over 10, so the final value is 0.35 ampere. So the answer is second one. Good. I saw Amnasuddin and Zainab Hussain had got these two answers. What about the others? This answer, second one. Anyone else who got second? So remember, when you say magnetic field, it doesn't always have to be just about magnetic field. It could be, it will relate to electricity as well, electricity. So you should be able to incorporate everything we have learned. Okay, done. So that's the first question in 2006. And then let's move on to the next part, that is a question from 2007. So what does this say? All right, now this, I think we will have to include a certain part to our note. I think I missed to include this to our note. So let's include this to our note. Sorry, yeah, 15th one. That is from 2007. An EMF is induced across the length of a wire when it is moving in a uniform magnetic field. This EMF does not depend on, right now, we studied, I think I gave that equation, but I forgot something very important. If your wire is moving perpendicular to the field, if the wire is moving perpendicular to the field, let me draw the field as well. Right, if you draw the field like this, no field, let's say the field is into the plane or something like that. We have a field which is going into the plane. Okay, give me a second, let me quickly mark this, and let's do a quick revision also, right? I want you all to tell me the direction of the current induced in this, or EMF induced in this. Now we have the magnetic flux density directed into the plane like this. Okay, and we are moving a wire in this direction, horizontally this way, and the magnetic field is into the plane. Now what is the direction of the current, or direction of EMF induced in this? Now there can't be a current in this, no? There can't be a current in this because the circuit is not complete. Circuit is not complete. What's the direction of EMF? Is it from top to bottom or bottom to top? Yeah, you have to use Fleming's right hand rule. Fleming's right hand rule. And when I apply it, it looks like this to me. How? It's my thumb. Right hand ruler. Thumb is directed that way, and my index finger must be directed into the plane. I'm talking about right hand ruler. So my middle finger, it is this way, it's pointed this way upwards, and that is the direction of who? The direction of current. That is the direction of the current. Direction of the current, if not direction of EMF. EMF in the sense direction of current. That is how the current is going to flow, and this is the direction of the motion or direction of velocity, and the index finger represents the direction of magnetic flux density. Okay, and what is this rule? What are we using here? We are using Fleming's right hand rule. Careful, not left hand. Fleming's right hand rule. Okay, now if current is supposed, now current will not flow, that current can't flow, actually current can't flow because the circuit is not complete. If you want a current to flow that way, there must be a temporary EMF induced. How? The temporary EMF induced should look like this. EMF, yeah, it should look like this. Induced EMF should look like this. So this point will be at high potential, this point will be at low potential. We can say that, but we can't say there will be a current. Remember, current will not be there, but if current had been there, that is how the current would have flowed. Okay, so that we know. That's number one. And what is the equation for that, people? The equation for that is the induced EMF. Hope you can remember. Let's say this has a length of L. It has a length of L. The what do you call that? The length. Yeah, the length of that is L. Sorry, the length of that is L. Then the equation for induced EMF is BLV directly. Induced EMF is equal to BLV. No problem there. But sometimes that wire might be creating an angle with the magnetic field. Sometimes the wire might be creating an angle with the magnetic field. Okay, then there's going to be a problem. What was he saying? Yeah, okay. Now for an instance, let's think of a situation like this, people. Wait a minute, I have to be very careful now. How do I put this? So we have to be a bit careful now. Imagine have a magnetic field like this, for example. How I have to show that they are not okay. Magnetic field like this, for example. This is the magnetic field, and now I have kept the wire like this. This we didn't study. Please include this in your note. Please include this part in your note. We couldn't include this in the note. I'm sorry. This is the wire now, and the length of the wire is L, just like the previous scenario. Length of the wire is L. No problem with that. We have a wire and it has a length of L. It is moving inside the magnetic field. I mean, length of the wire inside the field. That is also important. I can't just say length of the wire. That L, people, length of the wire inside the field, not just the length of the wire. So it's better to be on the safe side. I'll draw that properly. Just imagine that the entire wire is inside the field. Otherwise, technically, it's not going to be accurate. Careful. The entire wire has to be in the field. If you're going to use L, entire L, right? Fine. Now, how should the wire move in order to create a magnetic? In order to induce an EMF in it. In order for an EMF to be induced in, how should it flow? Now, current is going to go either up or down. It should move either in or out of the plane. The wire needs to be moved either in or out of the plane. And when you do that, you let's say there's an angle like this. There's an angle like this, theta. The angle is theta, no, people. Magnetic field is creating an angle of theta. See, theta. You cannot use this theta. Sorry, you cannot use this B directly. We have to use the component of B, which is what? perpendicular to that wire. This must be used. What is this? If this is b cos theta, this one is b sin theta. Now the EMF induced will have a different equation. Now here EMF induced will be equal to b sin theta LV. Okay. Wire should move with a velocity of v into the plane or out of the plane, into the plane or out of the plane, because one of the three, direction of motion, magnetic field or current, one of the three should be either into or out of the plane. So in this first example I gave, magnetic field was into the plane. Here none of them is into the plane. Now the current is going to be like this, magnetic field is like this, so velocity this time should be into the plane. Can you tell me, let's say here right, okay, let's do it this way. I'll put this velocity is this term. That means wire moves into the plane. Wire moves into the plane. Tell me the direction of where will we have high potential, top or bottom? Where will we have high potential, top or bottom? Wire is moving into the plane, right? Wire is moving into the plane. Okay. How are you going to use the rule, left hand rule? This time the left hand rule is going to be like this. Thumb must be into the plane. Thumb is into the plane, right? Thumb into the plane. Thumb and index finger in this direction, and middle finger is down for me, like this. If you use Fleming's right hand rule correctly, this is how the answer is going to be. Sorry, this is the index finger. This is the index finger, God, and this is the middle finger. So people, directions. This is going to be the direction of current, no? This is going to be the direction of current. If that is the direction of current, EMF must be this way. The battery must be this way. So here we have high potential, isn't it? Here we will be having the high potential. Here we will be having the low potential. Right? I think we are reaching completely out of the question, but I wanted to mention this to you. I forgot to mention that importance of the theta. I forgot to mention the importance of theta. So good. So few of you have guessed it correctly. Bottom will have the high potential here. If you use the right hand rule, that is how it's going to be, because if current is flowing from top to bottom, the battery should be like this, no? Right. Now the induced electromotive force, it actually depends on four things. It depends on four things, not just three things. It depends on four things, because the previous equation we use it when wire is perpendicular to magnetic field. Wire is perpendicular to magnetic field. All right, and this equation, when will you use it? Used when the wire creates an angle with the magnetic field. Okay, so let's quickly go through the answers now. Velocity of the wire, that's correct. Velocity of the wire is correct. Radius of the wire, no, it doesn't, right? Radius of the wire doesn't have anything to do with this. No, wrong. Length of the wire, yes, that is L, correct? I mean V, this is V, this is our L. And flux density of the magnetic field, yes, that is our B. And don't forget theta is also correct. The angle that the wire makes with the magnetic field, these are vectors, so that angle is going to be very crucial. Answer is second one. Anyway, I think you should have easily identified it as the answer, but in our note, I think I forgot to mention this. So please include this to the note. Please include this part to the note. I will just make a note of that as well separately. Must be included in the note. Right, good. So we have quickly done a revision as well. Done. And then people, next question. What about this one? Nice. Oh, another point to include the note and discuss it, not the note, but under Faraday's equation. Okay, under Faraday's equation, we define A. So here I'm going to tell something more important about it as well. Three identical circular wire loops are placed perpendicularly to uniform magnetic fields of flux density B. Uniform magnetic fields of flux density. The extent of magnetic fields, are different from one another in situation P, Q, and R as shown in the figure. Situation P, Q, and R in the figure. The extent of magnetic field as Q at Q, or in Q, what it is in the diagram Q, is equal to the area of the loop. Right, you can see that in the diagram, it's equal to the area of Q, obviously, yes. When the flux density varies with time, the same constant rate. When the flux density varies with time at the same constant rate. Read this carefully. When the flux density B varies with time at same constant rate. So what can I say? What can I say for PQR? For P, Q, and R, who is constant? Who is constant? Let's see. What is constant? Not omega. No. It is not rotating. No, Asna. Nothing is rotating here. What is constant? What is constant? Wrong. Not area is not constant. Wrong. It is dB by dt is constant. dB by dt is constant. dB by dt is constant. Okay, dB by dt. Here, same constant rate. When you say rate, you have to focus on dB by dt. Area is not constant. That's what I'm going to explain here. The induced EMFs of the respective wire loops are EP, EQ, and ER. Which of the following true regarding the magnitudes of EP, EQ, and ER? So in each of these wires, magnetic field is going to be electromotive force is going to be induced in people. EP, EQ, ER. And now we have to see what is the correct order. What's the correct order? So what do you think is the correct order? What do you think is the correct order? What is this question number? 16. What do you think is the correct order here? Right, let's start. Now I'm going to teach you something important here. If we haven't included that in our note, please include that also in the note under Faraday's law. Now, according to Faraday's law, we discussed, let's forget about the direction for the time being. According to Faraday's law, induced EMF is equal to d phi over dt. Guys, hold on. You try this question, will you? All right, sorry. Yes, now if we haven't included this in our note, please let's include it carefully. This is the equation according to Faraday's law. We study this equation. Induced EMF is given by d phi over dt, and that can be written as d over dt BA. So here they have clearly mentioned that magnetic flux is changing. So that can be written, A can be taken out, A dot dB over dt, because they have told the rate of change of magnetic flux density is constant. So this one. Therefore, if listen now, if dB over dt is constant, dB over dt is constant, guys. What can I say? What can I say? We can say that induced EMF is directly proportional to area. Proportional to area. So we find out guys inside the magnetic field. Inside the magnetic field. Sorry, people. I think I had a connection drop now. I had a connection drop. Can you hear me now? Hello? Okay, sorry. Yeah, I had a connection drop. So where is that? We were discussing this question, weren't we? We were discussing this question. This question that's a question from 2007, but unfortunately there was a drop in the connection, so we'll have to discuss this one more time. Where did I lose the connection, people? I was telling few things. First of all, we figured out that there are three identical circular while loops. So the area of the loop is constant, and they all have yeah, the extent of magnetic field is given. So the extent of magnetic field spread it's given. Extent of magnetic field blah 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 equal to the area of the while loop. Yes. The flux density B varies with time at the same constant rate. Therefore, we said for all three, for P, Q, and R, dB over dt, that is constant. dB over dt is constant. So we have to compare the induced electromotive force in each of them. Where the answers are provided. Now, according to we all know, according to Faraday's law, according to Faraday's law, according to Faraday's law, induced EMF, that is equal to d phi over dt, and instead of phi we can put dBA over dt, and in the question they are clearly mentioning about dB over dt, so we can say area dot dB over dt. If you take a common equation, we are trying to build a common equation here, right? But they have told that dB over dt is constant, people, but dB over dt is constant, so constant, so we can say the induced EMF, so induced EMF, that is actually directly proportional to the area, because they have clearly mentioned that this. So now we have to compare the this area here. Area here is what? The area here is not in the area of the circular loop. It is the area of loop inside magnetic field. Inside magnetic field. So that is the area of the loop intersecting the magnetic field. So if I mark those areas in blue color, no? I've used blue color here. This is the area. For P, this is the area. No? Or if not, we'll just draw a circle. I mean, wait. This is the area. No? This is the area. And for Q, this is the area. The entire loop is in the field. And for R also, this is the area. I mean, when you say area, the magnetic field and the loop both must intersect that. Got it, people? Now I can't take the area outside the loop, because this A is area of the loop inside the magnetic field. So that A, this A according to the definition, sorry, the A according to the definition, okay, so A should be either less than or equal to area of circular loop. Do you understand? Because loop should intersect the area we are considering. Hence, this is the area we have to substitute in this. So here for this is the area. For this is the area. And when you compare the areas, capital A's, it's obvious that area for P is smaller than area of Q and R, but for Q and R, areas are equal because the entire loop is exposed to that magnetic field. Therefore, now we just have figured out on top, but what is it, people? But here we have written on top, area of P is less than both areas of Q and R. Therefore, finally, we can decide this. You can say induced EMF in P will be the lowest and induced EMF in Q and R will be equal to each other. Therefore, what is the correct answer? Correct answer is fourth one. Okay, can I quickly get a confirmation whether you can see what I'm explaining here, people? I hope, yeah. I think earlier I lost my connection somewhere. I couldn't figure out where I lost my connection, but I hope you understood it now. Okay, after where you understood why the areas are not equal. Okay, yeah, careful. It's the area of loop inside the field, magnetic field. So we are done with question from 2007. It's a different one. So all three questions we have done so far different. This we'll do it later after we cover a little more. I think we can try this question. This is a good one. You also can try this. Right. How about this one, people? I think you can now. This is a question where you can implement both Lenz's law and Faraday's law. Part of a conducting square wire loop of side length 2 meter is placed in a uniform magnetic field as shown in the figure. If the magnitude of the magnetic flux density decreases at a constant rate of 0.8 Tesla per second. Careful, they have clearly mentioned magnitude of the magnetic flux density decreases at a constant rate of, okay, so dB over dt is given by 0.8. dB over dt is equal to 0.8 Tesla per second. And what else have they mentioned? Already existing magnetic field, already existing magnetic field. What is it doing? Reduces. How? Reduces into the plane. Reduces into the no, reduces out of the plane. Reduces out of the plane. Reduces out of the plane. Right. So what should happen if you have a magnetic flux density which is reducing out of the plane? So induced magnetic field must be how? Must be directed out of the plane. Directed out of the plane. Why is that? It is the already existing magnetic field is reducing out of the plane. So we also have to create uh, a magnetic field in the same direction to oppose that. That is Lenz's law. That is what Lenz's law says. If it is trying to reduce, you should not let it reduce. If it's trying to increase, you should reduce it. Therefore, if you induce B will be out of the plane. If you want B out of the plane, what should be the direction of the current, people? Direction of the current or EMF should be in this direction. EMF counterclockwise. So here EMF induced will be counterclockwise. EMF, I'll put it here. EMF induced will be counterclockwise. Yeah. So if I put it as a battery here, counterclockwise it is going to be a new. It's like now there will be a new battery here in this direction. Then we'll find the magnitude of that induced EMF according to. Now we have to be very careful. Look at the area. Look at the area. Only this part of the loop is inside the magnetic field. No? Only this part of the loop is inside the magnetic field. So you have to be extra careful now. I'll say area of loop inside magnetic field. Inside the magnetic field. How much is that? That is equal to half into area of square, na people? Half into area of square. We'll take it that way. I don't know, if not you can do it like this. I mean, you can take it as a triangle also. As a triangle, so it's normal. Simply we'll do half into the base into height, 2 into 2. So it is 2 meters squared, not 4 meters squared. Careful. In the previous question, we could consider the entire area, because the entire area of the loop, the entire loop was in the magnetic field. Now only half of the loop is in the magnetic field, so you have to take only half of the area. Hence, let's go to Lenz's law. Sorry, not Lenz's law, Faraday's law. According to Faraday's law, according to Faraday's law, we know induced EMF, that is given by d phi by dt. This time we can write phi as dB over dt, and A is constant, so A comes out. A comes out. So induced EMF can be written as A dot dB over dt. Now we found A on top right corner. You have A here. We have found it. That is 2, not 4. 2. dB over dt is given in the question, 0.8. And what is the answer? That is going to be 3.6. So no, 1.6 volt. 1.6 volt. This is the induced EMF. Remember, induced EMF. Is that what they're asking in the question? 1.6 is not even there in the answer. The net EMF of the circuit. The net EMF of the circuit. So how do you finish this question? So net EMF of the circuit. So net EMF of the circuit. We already have a 2 volt there. 2 and induced EMF should be subtracted to add it. Induced EMF, people. Huh? See, this 2 is also counterclockwise, no? Counterclockwise. 2 is counterclockwise. It's going to give a current counterclockwise. And now induced EMF, according to Lenz's law, it also gives a current in the counterclockwise. So they must be added. I have already put plus and asking you whether it should be added or subtracted. Anyways, it should be added. The previous one we had to subtract it because the battery was in the opposite direction. But this time you have to add both of them because they both will create a current in the counterclockwise direction. Therefore, the answer for this question will be what? 3.6 volt. Right? Okay. So question to question, the way you apply Lenz's law can be different. Interesting question. So here you have to be mindful about the direction. You have to be mindful about the area, because if you make a mistake in the area, you will get fifth answer. If you put 4 meters squared by mistake only, then you will get 3.2. 3.2 plus 2, 5.2 is also there in the answer. See. So this half is important. Area of the loop inside the magnetic field. Remember like that. Don't remember A as area. It's area of the loop inside the magnetic field. Okay, that is from 2009. And here we go. What is the answer for this question, people? 2010. We just studied a little while ago. We just studied about the graphs, didn't we? We just studied about the graphs. So tell me, what can you say about this graph? So they have given you a phi versus t graph, no? Phi versus t graph, and there are like 4 parts in the graph. Like now, phi t graph must be like the graph for what? Displacement time graph. No, displacement time graph, and the other part can be for this one is E, induced EMF, and we all know according to Lenz's law and Faraday's law, both combined, induced EMF E is given by minus d phi over dt. Remember, minus d phi over dt. Okay, so there are 4 portions in our graph. 1, 2, 3, 4 portions in our graph. And for those 4 portions, if I analyze them separately, one by one, if your phi versus t graph, listen to me carefully, if your phi versus t graph is a constant, if your phi versus t graph is a constant, when I say constant, it could be in the positive side or negative side, doesn't matter. It could be in the positive side or negative side, doesn't matter. As long as you have a graph like this, it could be either up or it could be down, doesn't matter, for both of these graphs. For both these graphs, I mean, wait, I'll tell you one, we'll draw them separately, right? Okay, now if it is either, if your phi t graph is constant on the positive side or your phi t graph is constant on the negative side, it doesn't matter because there's no change in it. No change in it. For both these graphs, if you if you consider the d phi by dt graph, that is definitely going to be what? 0. D phi by dt graph is 0. What is d phi by dt? The gradient graph. D phi by dt with time, it is going to be 0 because if there is no change in phi, then rate of change of phi will be 0. People, what about the EMF then? Induced EMF, what is the equation for induced EMF? That is a negative of this one. Induced EMF is the negative. Induced EMF E, that is minus d phi over dt. If d phi over dt is 0, then minus d phi over dt is also definitely going to be 0. So our E has to be 0 here. Induced EMF E has to be 0. And let's focus on the graphs. Wherever phi is flat, E has to be 0. Which answers are definitely wrong then? This is wrong. This is also wrong. This graph, this part is wrong. No, wrong. So here I can say E has to be 0. Here E must be 0 for flat, and here also E must be 0. Okay, good. And and then people, what about the other graphs, other answers? 1, 2 and 4 are wrong now. We have already figured out that 1, 2 and 4 are wrong. 1, 2 and 4 are wrong. Gone. Right, now we have to choose between 3 and 5. You have to choose between 3 and 5. So for Third one, what is the third one? This shape, the second shape. When your phi is like this, phi looks like this now. It's not exactly like this, but we can consider it like a shape like this. It is similar to a displacement time graph where the velocity is increasing in negative direction. So if you plot a d, if you consider d phi by dt for that shape, you will get a graph like this. And but d phi by dt is not what we need. We need E, which is minus d phi over dt, minus d phi over dt. So for minus d phi over dt with time, for this kind of shape, you will get a line like this going up. Line should be going up. All right, line should be going up. That is a second scenario. And the last scenario, it goes down. So let me draw that once again quickly. Now we have phi and t. The graph goes down like this. Not down. It is a negative side. Sorry, it's a negative side. The third portion, it is looking like this. Looking like this. So if it looks like this, what is the meaning of this one? It is in fact displacement in the negative direction and deceleration in the negative direction. This is like deceleration in the negative direction. Displacement time graph. So if you plot d phi by dt for this, d phi by dt for this, it will look like this. But that's not what we are looking for. We are looking for minus d phi over dt. So E is equal to minus d phi over dt. Then the mirror image of that is going to look like this. Okay, so the correct portions for induced EMF should look like this, and then this should go down. So it should go up and down graph. We have only the fifth one. The up and down graph, we have only the fifth one. I mean, it's not a perfect straight line, but it goes up and should come down. Everyone should go up, should come down quickly. Should quickly go up and quickly come down. This goes to negative side. That's not correct. The direction will not change like that. So yep, I hope you can understand. We just summarize these graphs. There are 7 types of graphs we can analyze for phi versus t, and the initial part and the final part are same, because phi constant, even though it's on the positive side, negative side, that doesn't matter. For phi versus t graph, only the shape matters. So based on that, we can decide. Just try to relate it to displacement time graph and velocity time graph. Phi versus t is like the displacement time graph. E versus t is like the negative velocity time graph. Compare like that. That way it's easy. Okay. So I told you at the beginning itself, there will be questions based on graphs, like I promised. Here we go. Done. Right. Before we go to the 20th question, let me show you another graph question. What about this one, people? Now, this is going to be very interesting. This is going to be very, very interesting. Right. Look at this graph. Look at this question. And see if you can do it. This is from 1998. I don't know how I missed it, but anyways, doesn't matter. 1998. So let me explain this one. A conducting rod is placed normal to a time varying magnetic field. If the magnetic flux density of the field varies with time as shown in the figure, which of the following curves correctly represents the variation of potential difference across the rod with time? So potential difference across the rod. Can you tell me another name for that? Potential difference across the rod. Can you tell me another name? Another name for that is induced EMF. Induced EMF. So we are changing the magnetic flux. We are changing the magnetic flux this way. And first and foremost, what we have to do is, they have given us B versus time graph. B versus time graph. Yeah. They have given us B versus time graph. So we have to draw dB versus dt graph. dB versus dt graph. Don't forget, listen to me carefully. According to Faraday's law, according to Faraday's law, what is the equation table? Induced EMF, that is equal to d phi over minus d phi over dt, because when you draw graph, you have to consider that minus also, according to Faraday's law and Lenz's law, both. Then we can adjust it this way, minus d over dt. Instead of phi we can put b over a, and a can be taken out. Therefore, I am getting minus a dot db over dt. Now in the previous question it was d phi over dt, but here they have given you b versus t graph. From that graph you can find db over dt graph, correct? So here this will, from this we can decide, that is that the fact that induced EMF is actually proportional to minus dB over dt. Okay, so from this graph they have given me B versus T graph. This is like the displacement time graph. From this graph, people, I can find out who dB over dt graph, that is like the velocity time graph, dB over dt. So what will be the shape of dB over dt graph? dB over dt, that is not the final answer though, careful, dB over dt. Acceleration again, so you can put two lines on the positive side, but this has larger gradient, so high gradient, and then slightly reduces to a lower gradient. Done. Okay, done. And after that it is a big reduction, so there should be a big reduction for some time. I mean the negative, it's like deceleration, it's like big deceleration, so we should have a high value and inside like this, and after that it increases at a slower rate, up, so maybe like this, yeah, and maybe like this, converting displacement time graph to velocity time graph, and once again lower like this, correct? So if you want to plot the graph for dB by dt, when they have given you B versus T graph, it is like converting displacement time graph to velocity time graph, people. Converting displacement time graph to velocity time graph. So if your displacement time graph is like this, you know how to convert it to a velocity time graph. B over T, gradient of B, rate of change of B over T. So this. But this is not the answer. What should I do, Mano? What should I do? I should draw the negative of this and consider that as my answer, because induced EMF is not depending on dB over dt, but it rather depends on minus dB over dt, remember, minus dB over dt. So we have to make this graph negative. Right, I'll write it. Induced EMF is the graph we are looking for, and that is equal to minus a dot dB over dt. So I have to A is constant, yeah, conducting rod A is constant, so dB over dt must be changed in the opposite way, and I have to plot everything I have plotted on the positive side to negative side, and everything I have plotted in the negative side I have to plot it in the positive side. So go to people, which answer do you think is the most suitable one? Huh? Do you have an answer like this, which maybe not exactly the same size of magnitudes and everything, but the, the shape like this? Which one? Can we go with the second answer? I think second looks fine, no? Second one, because second is the only one which looks similar to this. Second one, right? Good. Second one. So second one is the best option. Good. Some of you have got it, I think, even before I was explaining this. Very good. Again, the knowledge of gradients in physics. So it doesn't just stop after displacement time graph and velocity time graph. It continues on. You will have this in electric field when you want to convert what do you call that, electric potential to electric field intensity. Similarly, now in the previous question it was phi and t, but no worries, phi is equal to a into b, no people. When a is constant, variation of phi and variation of b will be similar. When a is constant, that's why I took it this way. Okay, all right, so good practice. Don't forget to change it upside down. I don't think there's a positive graph, and this is anyway wrong. You have to be cautious between these two. Now this graph, yeah, this is this graph, is it? No, still no. So yeah, if you know your basics right, you can, there shouldn't be any confusion, but you have to get this, make this connection correctly. So that is 1998 for you. Okay, fine. Then I was planning to discuss this question, but yeah. I think this we'll discuss this and we'll stop for today. At 2012 and the remaining questions, the ones which are remaining, we'll discuss later. For this one, will take some extra time, but I like this question because 2012 that will help you apply Lenz law. So you can, whatever we learned at the class, you can, apply. Right, let's discuss this quickly and then we can call it a day. Right, what is it? What this question all about? A light conducting loop is suspended. A light conducting loop means it's a very thin loop which can easily move. Light conducting loop is suspended freely and a half of the loop is inserted into magnetic field as shown in the figure. If the magnetic field begins to increase rapidly in strength, if the magnetic field begins to increase rapidly in strength, it should be in strength, no? In strength, what will happen? Right, let's analyze that quickly. So this blue color part, what it suggests is Lenz law, right? Already existing magnetic field, what does it do? Already existing magnetic field increases into the plane. The previous two scenarios it decreased. So this time, for the first time, it is increasing into the plane. So induced one, how should it be? So according to Lenz law, so I'll tell you, induced magnetic field should oppose that. If it is increasing inside, means induced magnetic field should be directed out of plane, because the induced magnetic field will always oppose the change of the already existing magnetic field. It will oppose the change of the already existing one. So I will mark it this way. Wait, induced one is out of the plane, induced one is out of the plane, people, like this. B induced. If B is induced that way, what about the current then? According to right hand corkscrew rule, this will be the induced EMF or induced current. Here current can be induced because it's a what do you call that? It's a circuit, complete circuit. And where will we have the current induced? The current will be induced here in this part of the loop, and it's going to be counterclockwise. Counterclockwise means the current is going to be induced this way, this way. Okay, people. So there's going to be a current this way. Wait a minute. I induced. Hope everyone can agree with me. Counterclockwise, no? Counterclockwise. So people, listen to me carefully now. If there's a counterclockwise current in the circuit, there's going to be a current flowing like this. There's going to be a current flowing like this. That current will be flowing like this. That current will continue to flow like this. Now, since that is a little too congested, let me draw that separately outside like this. And let's put the magnetic field. This is why I tell you the magnetic field must be thin. If the lines you use for magnetic field is thick, it's very difficult for you to mark the other information in that. So let's separately consider it like this. Okay, people. Now the entire loop is not inside the magnetic field. That's important. Now what will happen? There's an induced current flowing. We have figured out how to decide. We have decided the direction of the current like this. Now we have a loop inside magnetic field which is carrying a current. So what will happen? The loop now. What will happen to the loop? What will happen to the sides of the loop? They will experience something. What? They will experience a force, magnetic force. They will experience a magnetic force. And how do you decide the direction of that magnetic force? You can decide the direction of that magnetic force using Fleming's left hand rule this time. Fleming's left hand rule, don't forget. So here in this portion of the, now I think half of the loop is inside the magnetic field, so let's properly indicate that half of the loop, nearly half of the loop is inside, right? Okay, it doesn't matter. And half, even though half, okay, half of the loop is inside, doesn't matter. If you apply Fleming's left hand rule, you can find the direction of force. What is the direction of force here? Magnetic field is into the plane, magnetic field into the plane, and the current is towards left. Okay, so I'm getting a force downwards here, this way, and here current is going in the opposite direction, so I'm getting a force upwards. Okay, F1, and this is F2. F1 is equal to F2 because they both the currents are same, the lengths are same, so F1 is equal to F2. So F1 and F2 will cancel out each other. Cancel out each other. But there is going to be a cancel out each other. Cancel out each other. But there's going to be a force in the vertical part. What is the direction of this? The force acting on the vertical part, people. What's the direction of force acting in the vertical part? Now we'll add a note about this F1 and F2. How did I find the direction, people? According to Fleming's left hand rule. According to Fleming's left hand rule. Okay, so tell me now, yeah, the force acting here will be current downwards, magnetic field into the plane, therefore there will be a force towards right. There will be a force towards right, like this, F3. F3 is also determined using Fleming's left hand rule. So what's the resultant force? So resultant force, actually F3, okay, sorry people, there was a power cut, but anyways I managed to take a screenshot of it. Okay, can you see the screen? Can someone confirm, please? Can you see the screen? Anyone who is in the class? Who, Amna, Ravan? Yeah, thank you. Okay, right. So we just decided, we have figured out the fact that the force is going to act, there's a resultant force which is going to act in the right, towards right. So if there's a resultant force which is going to act towards right, then what's going to happen? So while loop will move towards right side, out of the magnetic field, So this question, in this question, we have to consider both Lenz's law and that first equation F equal BIL we discussed, Fleming's left hand rule, both must be used. Hence the answer for this question is going to be what? Fourth one, no? Fourth one. The answer for this question is going to be the fourth one. Answer is going to be fourth one. Where is fourth one? Yeah, fourth one. How are we going to apply Fleming's right hand rule? How? Direction of motion. Direction of motion. No, I'm not. Right hand rule. Direction of velocity means already it should be moving. If it was already moving, we can use the right hand. It is not already moving. But will it work? The right hand rule. Magnetic field is into the plane. Okay. What about the current then? No, you can't. That doesn't work that way. It worked that way. I don't think. No. You should first of all figure out where, how, in which direction it will experience a force. Which direction it's going to experience a force, and then based on that we decide. Because initially it's at rest now. All right. So I hope this question gave you a good comprehension about how to apply Lenz's law. So that's why Lenz's law is not just that equation. Remember, Lenz's law is how you apply, how you find out the current. That is important. All right. Good. I think we are running out of time, in the sense there's a power cut here, and yeah, we have covered enough I think for today. So let's stop it here, and let's continue discuss the remaining questions in our next session.